Okay, greens and salutes. This is my overview for chapter 11, okay, for this. And in this chapter, we're looking at how matter behaves. Solids, liquids, gases. What is up with all of that? So one of our big things that we had to look at is something called intermolecular forces. Okay, and I have to make it clear, this is not between atoms inside a molecule. That's kind of like a family thing. No, intermolecular forces means between the molecules. Now we have three basic kinds. Okay, then we talk about covalent bonding. We have hydrogen bonding. We have dipole-dipole. Okay, and then last but not least, we have the London dispersion forces. Okay, so those are our three basic kinds of intermolecular. Now there is ionic stuff with the ionic compounds. I am not going to worry about that here. I only work with these three because they work with covalent and they're pretty important. Okay, so intermolecular forces between the molecules, we have hydrogen bonding, dipole-dipole, and London dispersion forces. So hydrogen bonding, absolutely the strongest of them all. Okay, however, it is not stronger than what's going on inside a molecule. That's very different. Covalent bonding, polar covalent bonding, those are stronger in between atoms. It's like family. Whereas hydrogen bonding, think of it as best friends. Okay? And then here we have dipole-dipole. They're in the middle of the pack. The London dispersion forces are the weakest. Okay? So the London dispersion forces are the weakest, which makes dipole-dipole in the middle. Okay? So that's what's going on. Now, what else can we say about hydrogen bonding? Well, it can only be attracted to either fluorine, oxygen, or nitrogen. Okay? That's the thing about hydrogen bonding. Okay? Examples of that would include things like DNA. So we'll go example DNA. Okay? Dipole-dipole, on the other hand, it requires that you have a positive and a negative that are attracted to each other. So here's our positive, negative, negative, positive. This is the dipole-dipole. That's what it is, okay? And typically, we will find this in polar molecules. That's pretty much a dipole-dipole thing. Great for polar molecules, okay? And then London dispersion forces, it's weak in that it's a temporary dipole-dipole. And it switches off. And you might think about hydrogen bonding being best friends. Dipole-dipole, yeah, you're friends. You're not necessarily close, but you're friends. And the London dispersion forces, think of it as a flash mob, where you have a group of people who meet in one location at one time, they're together for 10 minutes, and then they disappear. And then they meet somewhere else at a certain time. So they're all gathered there. And that's what's happening with the London dispersion forces. This is typically, you find this in our nonpolar molecules, okay? Well, what do I mean by nonpolar? Think about CH4, for example. We can look at that. We can also look at things like oil, okay? Like oil, fat, wax, grease, all those, okay? So definitely, those are all intermolecular forces. Now, can you have all three of them acting at the same time? Yes, yes you can, okay? It's not an everyday thing, but yeah, you can have all three acting on between two molecules. That is very true. Okay? And some people would say, well, what difference would those intermolecular forces be? Well, it would make a difference for things like boiling points. So if we looked at water, how come water has such a high boiling point, okay, compared to so many other molecules? That's because of the hydrogen bonding. And we talked about how it affected climate here in Southern California. Okay, why is it that it is not freezing? Why can't you go and skate out on the Pacific Ocean right by the beach? It doesn't get that cold, folks. It just doesn't, because water takes a long time to absorb the heat during the day, and then at nighttime it slowly releases it. Compared to being out in the desert where you have hotter temperatures in the day, colder temperatures at night, because you don't have that huge body of water to affect the climate. Okay, so let's see. So things like evaporation, sublimation, condensation, it's pretty straightforward. Those are not chemical changes. It's not that the, water is still water, whether it is in the form of a solid like ice, in the form of liquid like we all drink, and in the form of gas, which is, we call it steam. It's still H2O. That hasn't altered. That's a phase change. So when you look at things like evaporation, condensation, sublimation, those are all phase changes. A phase is like liquid. Another phase is solid. Another phase is gas. And still another phase would be plasma. Sorry, we don't have water plasma. That just doesn't quite exist. Lattice energy, think of, when crystals form, okay, when crystals form together, they'll give off energy. That's what they call the lattice energy. Sensible heat, latent heat, I'm going to let you guys look that up in the notes. Temperature and heat, is there a difference? Yeah, absolutely. So if you think about heat is the total amount of kinetic energy that you would have in an object. Okay, in the notes it talks about thermal heat. Okay, but if you think about it, heat energy is a form of kinetic energy. So when we look at something like heat, it's the total kinetic energy in the object. Now when we look at temperature, that's the average amount of kinetic energy in the object. So let's take a look at this. How does that work? Okay, well, okay, I have 2 glasses of water. All right, one is pretty full. The other has less water in it. Not quite empty, but less. Now, for the sake of argument, we're going to say that they are both at 20 degrees Celsius. So we know that their average amount of kinetic energy in these 2 things of water are the same. But which one has more heat in it? Which one has more heat in it? Which one has a greater heat content? Well, the one that has the greater heat content is the larger glass, the larger amount of water in the glass. Why? Because if you think about it, if we had put these on the stove and they were at 10 degrees Celsius and we were heating it up, which one is going to require more heat energy to go up to 20 Celsius? This one or this one? Well, this is going to take naturally more energy to heat up to the 20 degrees Celsius. So you see, that's why you can sit there and look at the difference, okay, that you can have the same temperature but different amounts of heat in it. This has definitely got more heat as a result. Okay. Now, terms like fluidity, compressibility, diffusibility, permeability, again, you can get those out of your notes. Okay, can gases go and be permeable to things? Well, yeah, absolutely. If you put food in a plastic container and you put it in the refrigerator, and let's say you forgot about it and it's been sitting there for a few weeks, and at this point now the food is spoiled. Ugh. But the smell is a gas that's made by the food that is bad, and it goes through the plastic into the refrigerator, that when you open the refrigerator, oh my gosh, it smells so bad. What did I leave behind? Oh, look, it's that leftover salad. So yeah, gases can absolutely be permeable, and so can liquids. too. It depends on the material that's there. Compressibility, think about squeezing down. Gases are compressible because we can fill tires. We can make sodas with it. We can give the fizz in the sodas. Now, can we do the same thing with liquids? Liquids are not really that compressible, not compared to gas, because liquids are closer to being a solid. The molecules are more packed together. Okay, amorphous, okay, and allotrope again. Remember, OUS means full of, morph means body, so amorphous means not full of body. So things like glass, wax, okay, butter, those are amorphous. Their organization is not very obvious. It is disjointed. It's kind of in a confusion. It's jumbled up. Okay, whereas when we look at something that's crystalline, okay, when we look at something that is crystalline, when we look at crystalline, this is most solids, for one thing. Metals are also crystalline. Even if we shape the metal that we find in our cars, the phones, in frying pans, window frames, all those, it's a crystalline structure. Well, what do we mean by crystalline structure? Well, if we talk about crystalline structure, we're talking about something where there is there's an obvious organization to it. So there's an obvious organization to the crystalline structure. When we look at something that is amorphous, on the other hand, it's disjointed. It's not really making any sense. That's disjointed. Notice the difference in organization. This is crystalline. This is amorphous. Okay? So, to make that difference. Allotrope, okay, when we talk about allotrope, so I'm going to wrap up here. Allotrope. It's the same element, different organization. So it's the same element, it's different organization. So we can talk about carbon in diamond. Okay. We can talk about carbon being in diamond. We can also talk about carbon being in graphites. We can also talk about carbon being in coal. So all those, they're allotropes, but they have a different organization to them. It's how they are put together, which is why I keep saying about chemistry is God's Lego set. Okay, my time is growing short here, because I'm not intending to spend the entire time with this. So, if we're looking very fast at Chapter 11, we talked about the idea of intermolecular forces. We looked at they were between molecules. We looked at hydrogen bonding, dipole-dipole, London dispersion forces. Okay, we also looked at the difference between temperature and heat as well, looking at these two glasses of water, both the same temperature, but the one that has more water has more heat in it. We also talked about crystalline solids, like most solids, like metals, nice and neatly organized. And then we looked at amorphous, where you've got the stuff there, but it is not well organized compared to this. So amorphous things like wax, butter, glass is another one. Quartz is another crystalline. Okay, and then of course we talked about allotrope as we work our way through. Same element, different organization. We can look at carbon in the form of diamond, in the form of graphite, which you use in pencils, and then coal. All right, guys, I hope that this big overview would help bring things into perspective for Chapter 11. Okay, take care and God bless.